All right, so in this lecture, which I call 21.5 because we're filling in numbers, I would like to talk about a topic that seems to be perpetually confusing, namely boundary conditions. So boundary conditions come in many different varieties. In particular, we call them, for example, Dirichlet conditions, Neumann conditions. There's Robin conditions. Then sometimes we talk about strong and natural or weak boundary conditions. And then if you want to use physical terms, you can talk about force conditions and traction conditions and flux conditions and all of these sort of things. And what I would like to do is I would like to make a little bit of sense out of all of this zoo of names, where they come from, what they mean, and so on and so forth. So I would like to take this class on the issue of the theory behind this. So where do they enter the mathematical formalism? And then in the next class, come back to the issue of how we deal with this in practice, in finite element context. So before I start, I want to define these terms Dirichlet, Neumann, and Robin. So Dirichlet conditions are typically ones where, if we call the solution variable u, they set the value of the solution to some particular g. So let's say g is a given function, then u on the boundary, d omega, has to be equal to g. That would be something that we call a Dirichlet condition. A Neumann condition would be where we possibly have a multiple a times du over dn. So the normal derivative equals to something given, and the Robin condition would be something where we have a mixture of these two. So a multiple of the solution, b times u, plus or minus a multiple of the normal derivative equals to g. And you will see in the next few slides then where they all come into play. So I would like to start this whole discussion on the Laplace equation because we know everything about the Laplace equation and because we have sort of an intuitive understanding of how things work. So if you look at the Laplace equation, minus Laplace u equals f in the domain, and let's say you have Dirichlet conditions on the boundary, u equals 0, and in particular for now I would like to consider homogeneous Dirichlet conditions, so u equals 0, not u equals something. So for this one, we know, and you've seen this many times in the previous lectures, what the weak formulation is, namely that grad v times grad u equals v comma f for all v in the test space. And in that particular case, the test space v is v0, which is the same space that we look for solutions in. So u must also be equals to, or u must also come from this space v0. And v0, of course, is the space h10 of functions that have one weak derivative in L2 and are 0 on the boundary. So to understand where you go from there, it is important to remember that you can write this problem either in strong or in weak form, or that there's a third reformulation that is entirely equivalent, namely that the solution of the equation that we're looking for is in fact the minimizer of an optimization problem. So the optimization problem involves an energy, and the energy J is defined as 1/2 of the norm of grad u squared minus f times u, or the integral of f times u. And that comes out of physics. So in physics we often say, well, we write down, let's say, the energy of a membrane, and we would like to nature likes to find a steady state that minimizes the energy. And so what we need to do is come up with an energy functional as a function of, let's say, the displacement u of x and y, which would be the vertical displacement of a membrane. And if we write down the equations from physical principles of what we expect this energy to be, then we find that it's this particular minimization functional. And it is an entirely equivalent formulation to do it this way as to do the weak formulation as to do the strong formulation if the domain is regular enough, for example. So in this case, I can write it 3 different ways. Now, let us consider the case where I assume that I have non-zero boundary values. So I have, let's say, a membrane, and I want to compute its deflection u, its vertical deflection, under a force F, but now I want to have a non-zero displacement u equals g on the boundary. So in this case, you have seen this again many times in the programs that we've looked at before and in the formulas that we've had in previous lectures, that the weak formulation is grad v times grad u equals v times f. But now, of course, this u, the solution, comes out of a space vg that would be v must be an h1 function, and it must be equal to G on the boundary. And the question is, what is this proper space that the test functions come out of? So that's sort of not immediately apparent from this sort of formulation. Maybe we would say that V must be equals to, V must come out of the space Vg that the solutions are in, or maybe it is something different. So the question is, what is the appropriate formulation? Now let me walk you through this, how this works. So in this case, I would like to start the reformulation from the minimization function on, right? So we still are looking for a function u that now comes out of the space Vg that has u equals g as boundary values, and I would still like to find the minimizer of this energy functional, which is exactly the same energy functional as before. Now when I say I'm looking for a minimizer, let me call this minimizer u, then it certainly has to satisfy the following optimality condition, namely that the energy of u must be less than or equal the energy of any perturbation of this u. For example, u plus epsilon v for any direction v. Okay, so I would like to find a u that satisfies this particular equation for any u plus epsilon v in Vg, right? So the arguments of J are, of course, all of those displacement fields that have G as boundary values. And so one of the things that I need to ask is that u plus epsilon v is in Vg. And if u is G on the boundary, then that requires me that v is 0 on the boundary so that u plus epsilon v has the correct boundary values, right? So if u plus epsilon v has the correct boundary values g, but u is already g on the boundary, then v must be equal to 0 on the boundary. So if I reformulate this some more, then for differentiable j's, and this functional j is differentiable, then I can rewrite this as follows, that the optimality condition is that j prime equals 0. That means that, well, if you minimize something, then that means that the derivative must be 0, and the derivative is defined as this. And if you formulate this out and take the limit, then you will find that this is exactly equal to grad v times grad u minus v times f equals 0 for all v, and these v's are exactly those perturbations of this displacement field u that have the correct boundary values. So the way I think about this space from which the test functions come is it must be the tangent space. The tangent space is something like this. Well, in a nonlinear setting, for example, let's say my solution must be on this particular, well, it's an infinite dimensional space, but I cannot visualize things infinitely dimensionally. So let's say my solution must be out of this space. Let's say here is the solution. Then I need to evaluate the energy and make sure that the energy for all possible other functions on this space is defined. So what that means is that the perturbations u plus epsilon v must be tangent to u, right? And that means that the boundary values that v has to have are 0. So we call this the tangent space, and in this context here, that means that if u is in Vg, then v is in v0, v0 being, in this case, the situation that it's all of the h1 functions that are 0 on the boundary. So what happens if I ask that u equals g is only, or that u equals g only on a part of the boundary, let me call this gamma 1, and that I have Neumann boundary conditions on another part, gamma 2, well, in that case, I can write down the exact same derivation with the energy and its derivative, and I find that grad v grad u minus v comma f must be equals to 0, again for all v's, and the v's must be from the tangent space. So in this case, these are all the phi's in h1, but phi must only be 0 on, or needs to only be 0 on gamma 1. This should be gamma 1, not d gamma 1. Okay, so if u equals g on gamma 1, then v equals 0 on gamma 1, but not necessarily on gamma 2. So on a having derived this, now I would like to go through the process then how we go from the strong form to the weak form in more general settings. So let me say that I have this equation here, minus Laplace u equals f in the domain, u equals g on gamma 1, normal Neumann conditions du over dn equals h and gamma 2, the way I go to the weak form for this is, of course, as I always do, I multiply the equation with the test function v. I integrate over it, then I get v times minus Laplace u equals v comma f. I integrate by parts this term here, so I get grad v, grad u, and I get a boundary term, right, from the divergence theorem. And the boundary term has the form minus v times n dot gradient u integrated over the boundary. Now, in a case like this, where the boundary consists of two different parts, gamma 1 and gamma 2, I will write this integral, v times n dot gradient u, as a sum over integral over gamma 1 and an integral over gamma 2. And let me look at these terms separately. So, for the first term here, you remember that we had said that if u equals g on gamma 1, then v needed to be 0 on gamma 1. So this first term here disappears because v is 0 on gamma 1. And for the second term, that was v times n dot grad u, I know that n dot grad u, well, actually it's not equals to g, it should be equal to h from the condition up here. Okay, so I know that n dot grad u equals h. So u does actually not appear in this term anymore, only the boundary values appear, and I can bring it to the right-hand side. And so what I get is only the term that I have here already that survives, so grad v times grad u equals, and on the right side now I have a domain integral, v times f, and I have v dot, and this should be h, so v dot h on gamma 2. So this is the way we derive the weak formulation for boundary conditions that involve Neumann terms. I want to introduce a little bit of notation on this. So in a case like this here, where the test function is 0 on a part of the boundary and the corresponding term disappears, that corresponds, of course, to this case u equals g, and that is something that we call strong boundary conditions. So u equals g corresponds to a term that disappears because the test space is 0, or the test function is 0 in that form. Whereas over here, where I have n dot grad u, and I replace that by something that comes out of the boundary condition, so I should have replaced it by h, not by g. I will fix that in the formulas or in the slides that you will find on my website. So when I replace n dot grad u by h, and I bring it over to the right-hand side, that is a term that I call natural, right? So for this case here, these are the Dirichlet conditions are strong, and the Neumann conditions are natural conditions. What about Robin conditions? So if you have Robin conditions, they have the form b times u plus du over dn equals h. And then you go through exactly the same formalism again. You multiply this with the test function. You integrate by parts. You get a boundary term. You look at the boundary term again. On gamma 1, u equals g, so v equals 0. So this term disappears. And for the term over here, I get that n dot gradient u is, well, I should have put a 0 here, then it is equals to minus bu. So if I do this, then it stays on the left-hand side with a plus sign, and the solution variable actually reappears in the boundary term. So in that case, my weak formulation just involves a boundary term that involves u. Next situation. So what if I have a Laplace equation that has a coefficient in here? So the natural generalization of the Laplace equation would be minus divergence, and there's a matrix A times grad u equals f here. For this matrix A, we typically have to assume that it is symmetric and positive definite. So in a case like this, the question is, well, we certainly know what we do with the Dirichlet conditions. What would be the appropriate Neumann conditions? Well, if you do this, if you multiply by test function, then you will find that here is another mistake in the formulas. It should be a grad v grad u. And the boundary terms have this form. So for the term on gamma 1, I again have that v equals 0. And then I have a term on gamma 2. And what I have here is n dot a gradient u. So if you ask the form, what is the appropriate Neumann condition for this particular equation, you will find that it's not du over dn equals h anymore, but it is actually a du over dn equals h. So the Neumann conditions is not something that always have the form du over dn equals something, but they actually come out of the term that I have in the equation. So in this case, I would have that n dot a grad u equals h, and then that's the term that I can put into this equation in the second term here in the boundary condition. So over here, I would replace this particular term by h, and that means that these are the conditions that I can impose. Now, in a case like this, and actually in all cases, what you will find is that the Neumann boundary conditions typically are ones that correspond to physical facts or physical statements. So in a case like this, what it means is that, well, n dot a gradient u happens to be exactly the flux. So if that doesn't work with the example of the membrane, but let's say if you had a porous media flow where u would be the pressure in this case, then n dot a gradient u would exactly be the flux of material across the boundary. So we can identify the Neumann terms typically with something that comes from physics. Okay, so more general questions. Now that I've shown you that Dirichlet is typically a strong boundary condition and Neumann is typically a natural boundary condition that we can shove over to the right-hand side, is that always the case? So can we always do this, that Neumann goes on the right-hand side and Dirichlet stays in the function space? And the answer is no. It depends on the spaces and on the bilinear forms that we have. And let me give you examples. So if I consider the mixed Laplace equation, so the mixed Laplace equation is typically a model for flow in porous media where we say that P is the pressure. And if you allow me for a moment, think about bringing this gradient P here over to the right-hand side with a negative sign and multiplying through this equation with A. Then U, which I identify with the velocity of a flow field, U would be proportional to minus gradient P. Essentially what that means is that if I have an area of high pressure and an area of low pressure, the gradient points from low to high pressure, the negative gradient points from high pressure to low pressure, and the flux is going to be proportional to minus gradient P. That means something flows from where the pressure is high to where the pressure is low, and the proportionality constant is this A. So that's sort of the intuitive interpretation of this first equation. And then the second equation says that divergence of u equals f. That means that, in particular, if f is 0, no fluid gets lost. The divergence of the velocity field is 0. Or that I have some explicit sources where I inject water or get water out, for example. Now, the boundary conditions that I would like to impose in these sort of equations would be, for example, that I prescribe the pressure, P equals G, or maybe that I want to impose the normal velocity. And here I've chosen to impose 0 normal velocities, but it doesn't have to be. It could be anything here. So n dot u equals something on a different part of the boundary, call it gamma 2. So if you multiply this first equation with a test function v and the second with a test function q, and you add them up, and then you would integrate this term here by parts. So I get v times a to the minus 1u, that's the term over here. Then here, v times gradient p, which I integrate by parts. So I get minus diff v times p plus a boundary term, so term of the form v times n times p, n being the normal vector again, minus the gradient, minus q times gradient u equals minus q times f. Okay, so these are the other terms here. So the spaces that I need to consider in this case is that u is in h diff, right? I need to form the divergences of the velocity functions here. And I want that in this case, n dot v equals 0. Or if I wanted to do this more generally, u must be from a space ug, where n dot u equals g, and then the test functions would have to satisfy n dot v equals 0. And the pressure here is not quite correct either. So I realized that about a half an hour ago. What I really only need is that the pressure is in L2. So I don't need to separate into Pg and P0. So if I look at these terms again, so I split the boundary into integrals on gamma 1 and gamma 2. On gamma 1, I can replace the pressure by g. So I replace this term here by g, and then it doesn't involve the solutions anymore, so I can bring it over to the right-hand side. And if n dot u equals something, then n dot v equals 0. And so in this term here, this term disappears altogether because the test function times the normal vector is 0. So what I get is only a bilinear form or a weak formulation that involves, well, this term, and this term here. So they all go over to the left-hand side. I already had minus q times f. And out of this term here, I get another contribution on the right-hand side. So what you see in this case is that the Dirichlet condition p equals g actually appears naturally in this example. So that means that I end up with something where I can replace p by g and shove it over to the right-hand side. So even though it's a Dirichlet condition, it's not a strong condition, it's a natural boundary condition. Whereas the second condition, n dot u equals 0, or more generally, n dot u equals something, would actually be a strong boundary condition, right? It leads to a term that disappears because the corresponding test function is 0, or in that case, n dot v equals 0. So it's a Dirichlet condition, but it is a strong condition, but the first one, u equals g, is a Dirichlet condition that happens to be a natural boundary condition. What happens if, for example, you wanted to impose two different boundary conditions on the same piece of boundary? Okay, so let's assume, for example, you wanted to prescribe both the pressure P equals G and that there is no normal flux on that part of the boundary. Well, then you end up with a term here where you can replace P by G, but n dot v equals 0. And so that whole term on the boundary here disappears, and the bilinear form that you will find does not involve this G at all. So what that means in essence is that the boundary condition P equals G will not be enforced. It will simply be ignored. So that's a typical case where if you impose two boundary conditions, really only one of them can be enforced and the other may or may not be satisfied at the solution. So you will typically end up in a situation where you have posed the boundary condition, but it is not enforced. The solution does whatever it wants to do, and most of the time it will not actually satisfy that boundary condition. So you see from this example here that I cannot impose whatever I want. I can only impose what the bilinear form allows me, or what that boundary term in the bilinear form allows me to do. All right, moving on from the mixed Laplace, let me look at the Stokes equation. The Stokes equation has a much richer structure, and there's much more that I can do. So let me take the Stokes equation in the following form, namely minus eta times grad u, so Laplace u. Eta would be something like a viscosity of this fluid, plus gradient p equals f, and the divergence of u equals 0. So it's an incompressible fluid with a viscosity eta, and it is driven by a force F. So if I ask the question, what boundary conditions can I pose for this particular case? Then again, I need to find the corresponding bilinear form. So I multiply by a test function. I integrate this term by parts. I'm going to integrate this term by parts. And so out of the minus eta Laplace u term, I get eta grad v grad u minus v n dot eta grad u. And out of the grad p term, I get minus diff v times p plus n dot v times p. Okay. If I take this boundary term and this boundary term together, I get the thing that I have here in yellow. Okay, and so let me look at this in some more detail. So if I look at that particular term, I realize that I can do the following things. So for example, I could impose boundary conditions of the form u equals g on the boundary, which then would imply by tangentiality that the test function v on the boundary must be equal to 0. So in that case, that term would disappear because v is 0 on the boundary. Okay, and I just get only the domain terms out of in my bilinear form. The alternative would be that I prescribe not that what happens with this term, but that I prescribe what happens with this part of the boundary integral, namely n dot eta grad u minus p times the identity matrix equals to something. So that would be what we call attraction force. Like I have my fluid, and you think of maybe an ocean, or a bathtub, and there's an airflow going across it, and so you have a friction at the top of the surface. That's a traction. It pulls the fluid along. So in a case like this, the Dirichlet conditions would be strong, right? These ones here, whereas the Neumann conditions would be natural again because they go into the bilinear form. I would replace this whole thing in the boundary term by h and bring it over to the right-hand side. So that's a natural boundary condition. So that's sort of my summary, right? If I have Dirichlet conditions u equals g, then I put this into the space. U must be from ug. The velocity would be from u0. And in my bilinear form, or in the weak formulation, I have nothing that pertains to this g. Whereas if I have traction boundary conditions, Neumann boundary conditions like this, then I put that into the boundary term, and it ends up here on the right-hand side. Okay? I can do many other things with the Stokes equations, and so I'm not going to go through all of the details here, but if you want to read up more on this, there's a long introduction in step 22, for example. But one of the things that I can do and that I would like to talk through is what, for example, if I prescribe not the velocity on the boundary itself, but only the normal component of the velocity. So I'm going to say I allow any tangential flow, whatever it might be, whatever comes out, but I'm going to prescribe, for example, that there is no velocity through the boundary. So a typical case would be, let's say you have the surface of the ocean. On a large enough scale, what you certainly can say is that the tangential velocity may turn out to be whatever it is, but the normal velocity is 0, right? The surface of the ocean to first order does not actually move up or down. The surface of the ocean is whatever it is. So I would like to prescribe u dot n equals 0, and the tangential velocity is whatever it is. So if I do this, if I prescribe u dot n equals g, then again by tangentiality, the perturbations must be 0 on the boundary, namely v dot n equals 0. So if I look at the boundary term that I have over here, right, that's the thing that came out of integrating by parts. What I need to do is I need to split this v here. So I have as a test function v, and all I know about that test function is that v dot n equals 0. So let me split this v into its, so v is just a velocity field. I can split this at the boundary into its normal component, okay, so n cross n times v, which is the same as n dot v times n, okay. For that part, I know that n dot v equals 0, okay. And then I have the tangential part, which is the identity matrix minus n times v. Okay, about this term here, I don't know anything. I only know that the normal component of v is 0, but not about the tangential part. So this term is 0, and what remains is I minus n times v times n dot, and then here eta grad u minus pi. So this is a symmetric matrix. I can bring it over here, and what I find is that I get out of this term here v times I minus n cross n times the tractions, okay. And so then the question is, what do I do with this term? So in my weak formulation, I would now have, well, the term grad u grad v minus, what is it, diff v times p minus q times diff u, plus this particular boundary term that I had here that only involved not the full traction, but I minus n cross n, so the tangential part of it. So in essence, what that means is that if I look at the equations, then I will have to, or I have already imposed that u dot n equals g, and I will also have to say what this term should be, the tangential part of the traction. So I will, in PDEs, in order to make it well posed, what I have to do is I have to say what it is, right? So I will have to say that the tangential part of the traction is 0 or is h or whatever it is, but I have to prescribe it, okay? And so a typical way of dealing with this, let's say in oceans, would be that you say, well, the tangential part could be, for example, what comes from air friction. or it is what it is. So let's say I don't know anything about it, then I could assume that it just happens to be, let's say, 0 if there's no velocity or no friction that happens. So now you will ask, if that is what it is, then I need to identify this with physical concepts. Okay, so if I ask my favorite physicists, they will say, so in this term here, let's say, or let's just go back to the full Neumann conditions, is this something that has anything to do with a physical concept? So is this really a force, for example? And your physicist will say, no, it's not really. The actual traction force, let's say the force that a wind field exerts on the ocean, would in fact have this particular form, namely not n dot grad u minus pi, but it is in fact n dot 2 eta epsilon of u minus pi, where epsilon of u is not gradient u, but it is the symmetric part of the gradient, 1/2 grad u plus grad u transpose. You remember u is a velocity vector, so grad u is actually a matrix, let's say a dim by dim matrix, and I can take the matrix plus its transpose and take 1/2 of it. That's exactly the symmetric part of it. So the physicists say this here is exactly the physical term that describes what traction forces look like. Now in the Laplace in the Stokes equation that we just looked at, this is the term that disappeared, or that appeared when I integrated by parts. And so I'm going to say, well, what should I do with this? I mean, this is what I have. This is what I want to impose. Can I impose this here? And the answer is no, I can't. There's nothing I can do about it. It's just not going to work. I mean, the term that I want to impose, the boundary condition I want to impose, corresponds to a term that simply doesn't appear in the weak formulation of the equation. And so I'm sort of lost, right? I want to put this somewhere into the equation, but there is no place to put it. And furthermore, the term that is there, I need to do something with it. So the equation that I showed you doesn't work. If I want to impose traction boundary conditions, then the Stokes equation that I showed you is simply not going to be the appropriate model for it, right? So let's say physically, I mean mathematically, I can say, well, let me impose n dot eta grad u minus pi. That is the appropriate boundary condition for this equation. But it's not what the physicist wants to tell me. So what I need to do is I need to reformulate the Stokes equations. Namely, I need to say, instead of the Laplacian here, I need to have the equation minus 2 eta divergence epsilon of u plus grad p equals f and diff u equals 0. Because when I take this particular formulation of the Stokes equation, then the corresponding weak formulation after multiplying by test function, integrating by parts, in fact has a boundary term that looks like this. And lo and behold, there is a term here that is exactly the one that I need. This is the one that I wanted to replace by h. Okay, so in that case, if I take these equations here, then I can do what I want. So you will say, well, that's sort of a bad trick. I mean, we started out with the Stokes equation, and then we couldn't do what we wanted to do physically. So you say, well, let's just solve a different equation. Well, that's not typically what we want to do, right? I mean, the equation must still be physical. I mean, it's not like I can just change the equation because I don't like the boundary condition. But if you look at this closely enough, you will realize that the equations are actually the same. So in particular, if you look at the original equation, it had minus eta Laplace u here, and now I have minus 2 eta divergence epsilon of u. They're actually the same, because if I look at this term, 2 eta diff epsilon of u, so epsilon of u was grad u plus grad u transpose divided by 2. So the factor of 2 and 1/2 already disappears, and what I get is eta diff gradient u plus eta divergence of grad u transpose. Okay, so diff gradient is Laplace. That gives me this term here. And if I look at this term here closely enough, what you actually find is the same as the gradient of the divergence of u. Well, but divergence of u is 0, so this term disappears. So what you find is that in the domain itself, the two equations are actually the same. right? This term here in the domain yields exactly the same term as we have up here. And the only difference is in the boundary conditions that I can impose. So for the first equation, I can impose this boundary condition, whereas for the second equation, I can impose this boundary condition here. And it turns out that that is exactly the physical term. So if you do not care about Neumann-type boundary conditions, if all you want to do is prescribe the velocity, you can choose one or the other form. But if you do want to impose traction boundary conditions, then you have no choice. If you want to have the physical traction boundary conditions, you need to choose the form that has epsilon of u. So you see how we can play with this, right? That sometimes we need to reformulate the equation in such a way that the boundary terms that comes out after integrating by parts is exactly the one that we need, right? Because that's the one that we can replace when we integrate by parts and then want to bring something on the right-hand side. So to sum this up, boundary conditions are a little bit complicated because there are so many different variations of what you can impose. You can impose the value, the derivative, some mixture of those. You can impose normal components of the boundary values and so on and so forth. In almost all of the cases, you can resolve these sort of questions if you go through the process of multiplying by test function, integrating by parts, and then seeing what the corresponding term is that comes out. And then there's two options that you have. One would be that you can impose strong boundary conditions. And strong boundary conditions mean that there is some part of the test function that you can set to 0 because it needs to be tangential to the solution space. Okay. So in that case, the term just disappears, or at least part of the term disappears, like in the case where u dot n was equal to something. Or that you have natural boundary conditions, which means that something that has to do with the solution is equal to an expression that you know from the boundary condition. You replace it by the boundary value, and you bring it to the right-hand side of the weak form. And in both cases, you end up with the same term on the left, but you have either just the domain force on the right, or you may also have a boundary force on the right-hand side that provides a forcing of your system. So that's sort of the theoretical part of boundary conditions, how we think about this, right? That it always comes from the strong form. You integrate by parts, you get a boundary term, you see what you have to do with that, and then you massage it until it matches what you need. Now, the next question, of course, would be, how do you actually do this in practice? So if I tell you solve the Stokes equation with these particular boundary conditions, what does that mean if you want to implement it, for example? And that's something that I'm going to discuss in the next class, but we'll get there.